Okay, good afternoon, everyone. So I think there are still a couple that are gonna join, but yeah, I think we could get started. So this morning session, I think you guys seen we mainly focused on a bunch of our embedded processing types of products, and then started to give like a brief overview of some of our analog, starting with our logic devices. And this entire afternoon session, I believe, will be mostly focused on some of TI's key analog devices or analog solutions. But for me, actually, for my session, it will be somewhat different. So I won't be really going into any specific products or specific TI products or promotion for TI products, but will be more on an application basis. So this presentation is actually prepared by our Power Design Services team. So they're a team within TI that do power designs for our customers and do our reference designs as well that you can find in ti.com. So this will be more of an interactive session. I would appreciate if, we could, there's some questions, and if some people can help answer, it'll be great. So to get started, I'm Alfred Lohico. I'm the FAE, or the Field Applications Engineer, based in the Philippines. So I'm actually also assigned recently to support some customers here in Thailand. And it's a great opportunity for me to be here to be able to present this topic to you guys. So my topic actually for this afternoon, to start off this afternoon, is common mistakes in DC to DC converters and how to fix them. So before going to the brief agenda, I just want to get an idea from the crowd here today. How many here has had experience in designing DC-DC converters, specifically like buck converters, boost converters, and such? Can I get a show of hand? Okay, so we do have some, which is good. So I assume the rest here, this may be a topic that not be maybe new to you guys or new information. But yeah, this is basically like a easy go-to guide or a common mistakes and how to design with our DC-DC converters. So for the agenda, we'll be going first with a quick overview. So just to give an overview of what is a buck converter specifically, since it's one of the most common DC-DC converters used in designs today. And then next, I'll be going through 10 common mistakes and how to fix them. So it is broken down into 5 broader topics. So the first is more on the converter capability and the part selection. And then next is the component selection around the device. And then next is the feature settings. So the different features of a converter to consider. And then board layout. So what you should consider in your board layout when you design with your DC-DC converter. And then measurement techniques to get the optimum measurement when you test your design. And in summary, summary of what we have discussed in the end. And a quote from someone unknown saying that, learn from the mistakes of others. You can't live long enough to make them all yourself. So this is like basically a guide for the mistakes that we've learned, so that you can also learn on your end and don't have to repeat the mistakes again. Okay, so just a quick overview for what is a DC-DC converter. So basically, a DC-DC converter is usually used for point-of-load regulators. So point-of-load meaning connecting from a bus voltage from either 5 or 12 volts, dropping down to 1 volt or 1.8 volts, connecting directly to a load. There comes the phrase point-of-load. So buck converter is the most common topology or most common architecture used for this type of approach, from dropping down from a higher voltage to a lower voltage. Here in the bottom left, you could see the different switching states of a buck converter. And then in the right, you could see the steady state waveform. So for the first state is when you turn on the high side switch, so the Q1. and then Q2 is turned off. So you could see that the voltage will be connected directly to the switch node and connecting to the output inductor. This results in charging the output inductor current, ramping up the output current. And then when you switch to the next state, where the low side switch turns on while the high side switch turns off, this would discharge the output current from the inductor out to the load. So basically the output current and the output voltage is an average of the input voltage and on both states. So yeah, to get started. So first situation. So this is a buck converter where we're seeing some jumps on the output. So basically this is with the output of 1.2 volts, 0 amps, so no load output. And then switching frequency is at 1.2 megahertz. And this is using a forced conduction, continuous conduction mode. So it has a stable or fixed output frequency through the entire load. So as you can see here, at 11 volts input, you could see that switch node that there's a steady switching with the output with a steady ripple. But when you increase the input voltage, you see a ripple on the output or a drop. And then suddenly there are some skipping pulses on the switch node. And as you further increase the 12 volts input to 12 volts input, this occurs further. So anyone here has an idea why this is happening in this design or in this buck converter design? The output capacitor. So that can also possibly occur. But for this case, it's not. It's not the situation. So good guess. Yeah. Anyone else? Yes. It's skipped the pulse, right? Yeah. So what do you think is causing this? Load current. But for this one, actually, it just keeps at 0 amps. So there's no load being put on the output. Okay. So yeah, good guesses. So actually the answer here is the minimum on time. So there's a restriction for every buck converter in terms of the on time that it can handle. So this one, as we increase the voltage on the input, the on time is getting much narrower for the switch node, that it could not handle it anymore. So the minimum on time is already being violated. And it cannot switch to, narrow enough for the switch node pulses. So what you consider in the minimum on time is actually the switching frequency and the output voltage, and the ratio of the output voltage to the input voltage. So as you can see here, this one is at around, the minimum on time is 83 nanoseconds. So this is one thing that you should consider, mostly on the duty cycle considerations. So when you design a buck converter, you need to make sure that first the switching frequency that you use can meet the minimum on time of the device. So for this one, this specific part, the minimum on time, yeah, we had it, this is like a spec in the datasheet for typical at 90 nanoseconds, but it can reach up to 130 nanoseconds. And this minimum on time is greatly affected by both the input voltage and the ambient temperature. So those are some considerations that you should do. And then if ever this minimum on time is violated, yeah, you could see some skip pulses, change in the switching frequency, and also the output can be unregulated, as you can see earlier. Sorry? Yes, of course. But this one, of course, this is for like one of the buck converters where the drivers also integrated already in the device as well. So you have to consider it. Yes. Okay. Yeah, good. So next, so which part here? You could see two thermal captures, both with conditions of 12 volts input and then 1.8 volts output with 8 amps, and then 700 kilohertz. So which of these two devices do you think is an 8 amp part? So one is measured at 59.6 degrees. The other is almost 20 degrees hotter. So which part is rated at 8 amps? The left or the right? Who thinks the left? Okay. Who thinks the right? Which part here is 8 amps? The rate of the part is 8 amps. So, yeah, basically this is a trick question because both are rated at 8 amps. But you could see that they have different performance. So one is hotter. Yeah, you could see 20 degrees hotter than the other one. So this is something that you should also consider. You could see in this part, in terms of the input voltage range, current rate, the size, they're all the same. But the difference comes in the RDS on. So this part B has a higher RDS on, almost double of the part A. That's why it gets much hotter. And then also the power loss is also higher. So what you should consider in terms of the part that you select, you should consider what's the average current. So actually both parts can support 8 amps, but you should see if your application requires 8 amps continuous, then you should choose a lower RDS on part. But if it just peaks at 8 amps for a short time and then usually operates at less than 8 amps, then you could possibly use the part B. So those are some considerations that you should also consider. And then we do have also a tool called WebTherm. So this is our online tool. Yes, true. How much efficiency you want and also your load requirements, your current requirements. Yes, higher efficiency also, but the price, yeah, is the concern. So it depends on what are your design needs, basically. Okay. So moving to the next. So this is the inductor current. So this is a waveform of the inductor current. Can somebody tell me what's wrong with the inductor current here? It's, sorry? Sharp, goes up very sharply, and then it's not the triangular, it's sawtooth. It's not sawtooth. Correct, okay. So anyone know why this is happening? Very good, yes. So this is, inductor current saturation. So this happens when, you could compare here. So for an inductor without saturation, you get the perfect sawtooth waveform. So definitely have to consider the inductor selection. So you have to first consider the core permeability. So lower core permeability, you get saturation. And then for causes of peaking in current waveforms and hard saturating cores. So you have to select also the right core, depending on your application. So for hard saturating cores, these are usually ferrite cores. And then low saturating cores are usually like metal alloy cores. So to avoid this, you could consider to use low saturating cores instead. And then of course, for the saturation, this can cause damages, either to the converter, can cause premature overcurrent protections, so your device can prematurely switch off, and then also limits the converter output current as well. So you definitely should consider, when you select an inductor, should consider a part with a soft saturating core as mentioned. Okay, so next, so for the inductor selection part, so this is the second part. So in this thermal image, you could see that the IC, this is the IC, and this is the inductor. So you see all of the heat is going into the inductor. It's reaching up to 53.8 degrees C. So any reason why do you think this inductor is getting too hot in the design? Okay, that can be a possible consideration, but no, it's not the. Sorry, the efficiency. The core loss, yes. The core loss is causing it, correct. So yeah, it's usually because of the inductor selection. So the inductor chose here is has a very large inductor current that goes through it. So this design used a 240 nanohenry inductor. And when you choose a higher inductor, like a 1 microhenry, you could have much lower heat dissipated on the inductor. So yeah, it's because of the high core loss, because of the low inductance that's seen. So in terms of inductor selection guidelines, so you should consider basically first the main rule of thumb when you select an inductor is the current ripple. So you should design your buck converter considering the around 15 and in between 15 and 40% of the max load current. So using this formula. So for converters, they use a rated load current for the device. And then for the higher inductance tends to possibly increase the peak efficiency. So you could see here with the higher inductance, with this 2.2 microhenry, you could get a higher peak efficiency, but higher peak efficiency with that. Yeah, I mean full load efficiency. My bad. But of course, with the higher inductance, you get the higher peak efficiency because of the lower core loss. So this one is an example comparing different inductors. So 0.68 microhenry, 1.5 microhenry, and 2.2 microhenry, and all from the same size, same vendor, comparing the performance of the efficiency. Okay, so part number 4. So what's causing the output oscillation? So you can see here, this is a 10 volt input, 1.2 volt output, 8 amp load step. So there's an 8 amp load step up. You could see on the V out, there's a drop, which is expected, but you do see oscillating coming out after the load is applied. So what do you think is causing this oscillation on the output? The change of load? Yes, it's impacted by the change of load, but what is possibly causing it to have that oscillation on the output? There's something that's not considered, or that you should consider in your design to avoid that oscillation. If you improve it, it will remove the oscillation. So what do you think? Yes, okay. So you're correct. So it's from the capacitor. So on the input, actually, specifically on the input capacitor. So the decoupling input capacitance is not enough. So here, this is comparing. As you can see, this is a measurement of the input voltage. You could see when the load is applied, it also goes through a similar type of oscillation with the same frequency as the output. So this is because, yeah, of the lack of the input cap. So you should ensure, this is a comparison now, where the same input voltage load step up. This is without the bulk input capacitance, and this is with the bulk input capacitance. So you could see that the input of voltage is not anymore oscillating, and the output voltage is also not oscillating as well. So you have to ensure that your bus converter is designed to be able to handle these type of large load occurrences. This one is for the input mostly, yeah, because of the very high load that was applied. It affected the input stability because you don't have any input bulk caps. If you don't use any input bulk caps, it could really affect the output as well. Sorry? The inrush, yes, that's right. So yeah, we usually in testing, so sometimes when you test one of our EVMs, sometimes you'd also require to add additional input bulk caps to avoid this type of, when you especially do load testing. So this is the second part. So this is removing the input bulk caps again. So you have to consider that. It doesn't have the input bulk caps. With a 9 volt input, 1.2 volt output, 8 amp step load, the output actually, in this situation, it drops directly to 0 and then ramps back up when the load is placed. So why do you think this output collapses after a load transient? Okay, so this is what happened. So that's why this image is shown, because usually for input box, we connect the input directly to the enable pin. And because for this situation, it actually trips the under voltage lockout of the device. So same situation, whereby adding that input bulk capacitance, you could be able to avoid tripping this the enable pin falling below the UVLO rating of the device. So mostly the one showed earlier is more on the input capacitors, but of course for output capacitance as well, you should always ensure that you have enough decoupling capacitance for both the input and the output. And then for the type of capacitor also used, you make sure that you do not use or do not replace your low ESR caps with high ESRs, because it's cheaper. Because this can also definitely cause some instability in your design, and also can definitely increase by a factor of 4 to 15 at negative 40 degrees C. And also the selecting of the output capacitance with load transient requirements should be also accounted for. So next, so this is for the switch node. So you could see here at the switch node, for 17 volts input, 1.8 volt output, duty cycle is only 11%. But you could see that the switch node has a narrow, wide, and a narrow waveform. So what can possibly be causing this in a buck converter design? Any guess? Sorry? Load transient? No, it's not because of load transient. I think it didn't put note here, but I think this is without load. Yeah. Okay, so mostly this can occur if you have a very poorly compensated design. So as you can see here in the gain phase margin graph, this design only has less than 5 decibels for the gain margin. So at the zero crossing of the phase margin, you could see from zero crossing to the gain margin, it's around less than 5 decibels. So a practice or common practice is to have at least 10 decibel margin across all operating conditions. So this one is a better compensated design, where at the zero crossing you could see it exceeds around 13 decibel gain margin, and you could have a more stable switch node. So relating to this, so this is for an output. As you can see, the switching the switch node is stable. But the output, you could see there's an oscillating 40 kilohertz oscillation on the ripple of the output. So in terms of the design, it's stable on an EVM. So this was tested on our EVM with the same specs done on a specific application or actual board. But they see this type of oscillation on the actual board. In terms of the phase margin and also the gain margin, we have enough gain margin here in this design, 16.7 decibels. And then simulation, this is the simulation. It shows that we have enough phase and gain margin. So what can possibly cause this type of oscillation on the output? The tolerances of the parts used, good guess. But when you compensate, it can, yes, that can possibly be a consideration. Of course, the tolerances may be exceeding what was initially designed, because of course in the simulations everything is ideal, right? But this one also tested in an EVM, so you tested with actual parts also. So it occurred when you used it in the actual design. So No, use in your actual board. Yes, in your design. Mm. 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 Oh, yeah, that can be definitely be considered also there. Actually, for this one, for this situation, so yeah, when they designed it on board, they actually added some additional filtering on the output. So this one actually cost this. So this is with they added a ferrite bead on the output and a capacitor to add an additional filtering on the output pin. But yeah, this one cost some like a second stage LC filter that was that caused some instability in the design. So comparing here, you could see in the solid lines, this is the solid line here that's black is the expected, the one shown earlier. But when they measured it with this external ferrite bead, it actually had a spike here on this end. No, they didn't consider it before. So perfectly. Yes. 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 It's so confusing. Yeah, but actually, I do have I do have experience with some customers where they did try to follow the EVM design, but when they looked at the output, they did add some additional filtering because they thought they needed it. But yeah, yes, you should resimulate again with the values. Yes, that's correct. That's correct. So you definitely have to also consider, as mentioned, yeah, you should design for the compensation with the actual output filter that you're using. Yeah, out of the box. Yeah, there's something wrong. Yeah. Yes, out of compensation. Yes. Yeah, but that can happen. That does happen actually sometimes. So something to consider also, especially when you design with their buck converter. Yeah, greatly noted. So okay, number 6. So why does the converter does not why doesn't the converter start up? So you could see here, this is the output. So you could see that it always it tries to start up, but it doesn't completely start up and it droops down again to 0 and then restarts again. So what can possibly be causing this to the converter to not start up properly? Okay, power limit. Any other guess? In the capacitor. Okay. So actually, yeah, it does have to deal with the output capacitor. It's mostly for it's very large output capacitance on this device, and this is actually triggering the overcurrent of the device. So you have to make sure that your output capacitance selection does not trigger this what you call overcurrent limit also of the device. So as you can see here, as it starts up, the current goes up, shoots up, and then it triggers it, so it triggers it to shut down again. And it keeps repeating because the device has like a hiccup auto restart process. So it continues, it starts up, shuts down indefinitely. So definitely this one, to be able to avoid this, you should also select the appropriate soft start time of the device. So to avoid input voltage sag due to inrush current, you also need to estimate the converter input and output current by using these formulas here. And then to avoid overcurrent protection limit, you should make sure that also the sequence startup of the supply rails is also aligned with that as well. So this one is a better, this is by utilizing soft start, because the ramp up is slow, it would not be, the device would not trigger the overshoot that you could see in the output capacitor. And it can start up properly. So next, so why is there a large switch node ringing? So you could see here in the switch node, in the switch node, yeah, for this one, you could see there's a ringing that where it overshoots up to around 10 volts. So why do you guys think that this occurs? Sorry? Damping. Um, yeah, that can be considered. Uh, but there's something else in terms of the design that maybe was not included. Maybe that's the clue there. Inductance. Okay. Oh, the trace of the inductance. Good guess. Mm. The capacitance. Okay. Yeah. So it's more on the input decoupling capacitor. So this one is a design actually rarely would occur, but this one, just for an example purpose, it doesn't have any input decoupling caps. So you could get very drastic overshoots on your switch node ringing. To be able to fix this, so by adding the capacitor, it also is important to note the placement of the capacitor. So it doesn't mean that you add one capacitor. If it's far away from the device, you could still get very high overshoots. But by moving it closer, and then by adding a 0.1 microfarad capacitor much closer to the part, you could drastically reduce it by half, comparing to with none. And this specific IC actually has two input voltage and ground on both sides of the IC. So if you also add on the other side, you could drastically reduce it even further. So of course, in terms of the layout, you should definitely understand the layout parasitics, as you guys mentioned. So definitely you have to consider minimizing the loop areas and keep the components as close as possible. So for both the input side and also even the output side, the switch node side. So this is like an example of optimizing your layout. So in terms of the schematic, if you can bring everything much closer to each other, the input caps to the switch node, that would be much better. So this can definitely avoid large switch node ringing, and which can result to EMI. And to keep noise sensitive analog pins, so like the feedback pin and also the compensation pin, make sure these routes or your layout, in terms of your layout, is away from very noisy pins or traces like the switch node and also the boot. And you can also definitely add a snubber or a boot resistor to control or slow down the switch node slew rate. Okay, so this one, we're moving more also, in terms of the layout side. So why is board A 10 degrees C hotter than board B? So you could see in board A, we're measuring 62.6 degrees C, while board B is at around 52.2 degrees. They are using the same parts, the same designs in terms of schematic, but you can see that there's a difference when you compare both designs of in terms of the heat pad. Okay, yeah. So actually, if you look into the layout or the thermal, you could see that there's somewhat like a line here. It's like somewhat limiting the thermals to properly dissipate comparing to the port B. So this is mostly because of not really the heat pad, but because of traces that's going through the ground plane. So you have to make sure that when you design your layout, you could see that to be able to prevent, to be able to properly dissipate the heat across your board, you should make sure that there is not no traces on the bottom layer of your board. And then by removing these horizontal traces for a more solid bottom layer, this reduces the IC temperature on board B. So this is comparing with the top temperature. You could see that the hottest component in the board B is actually moving to the catch diode. So in terms of layout considerations, you should definitely have a very strong or solid ground plane for better heat dissipation. You should use thermal vias to spread the heat properly across the heat pad. And then, as mentioned, you highlighted, thermal pads is a very big consideration that you should do here. So in our data sheets, we provide these thermal footprints on how we recommend to add the vias for the heat pad to properly dissipate the heat. Okay, so last two. So for number 9, so which output measurement is right? So you could see here, both are measured on the same design, same boards, but you could see for the output of the first one, it's much noisier. They are both AC coupled in terms of the measurement, but you could see here in the first one that there's a lot of spikes comparing to the second one. So can you guys think why the measurement in the first is different from the measurement in the second? Okay, so for the noisy measurement, first, if you compare it with you could see here, this is actually being measured along with the switch node. So they're using the same scope with the 2 probes connected to the same board. You could see here that the switching or the noise is affected by the switch node. So this is actually noise that's picked up from the second channel. And it's because it's using, you're using the ground cable of the oscilloscope probe. Another thing to note here is that for the first waveform, there's no bandwidth limiting used. So usually it is idealistic when measuring your buck ripple is to put a bandwidth limit. So ideally 20 megahertz bandwidth limited is recommended. And you could see that the switch node probe was also removed during the testing. So you could get a much cleaner read on the output voltage. So to consider, you have to make sure that, as mentioned, the way you measure the output is very critical. So by doing a tip and barrel mode, rather than using the flying ground lead, you could get a much cleaner signal on the output. And then make sure you probe the sockets for the prototype. So you probe directly on the output. And then, as mentioned, limit with the bandwidth of 20 megahertz. You could use the full Y scale axis to get a better resolution. And then you have to also consider, if you're measuring very small ripple, you can consider using a 1:1 probe or active probes in the measurement. Okay, so for the last, so we have 2 parts for the last one. So this is more on the Bode plot measurement. So why is the Bode plot not smooth? So you could see here, compared to the previous Bode plots that we provided, it has a bunch, some shoot-ups, especially at the higher frequency range. So what can possibly be causing this these shootouts at the higher frequency for the Bode plot? Okay, so for this one, specifically for this type of application, the signal injection is too large. So the signal injected to the device during the Bode plot measurement is too high. So the large injected signal results in the pulse skipping at the switch node, as you can see here. For the second part though, so this one is using a similar design where they decreased the signal injection, but you could see that there's a lot of noise or unclean signal measurements, especially at the low frequency side. So why is this not smooth on the low frequency? So this one is an opposite to the one earlier. So this one, the signal injection to the part is too low. So because of this, the signal to the noise ratio is too low, and the noise is overtaking, especially at the lower frequency side. So at low frequencies, the gain of the loop attenuates the injected signal. So it overcomes the injected signal that you used. And increasing the integration time or using lower frequency IF bandwidth helps to filter this noise better. Okay, so yeah. So in terms of optimal signal, small signal injection for getting a cleaner body plot. So this is using the right amount of signal injected to the device, where you can get a much smoother body plot. So yeah, as mentioned, if you use too large of a signal, it glitches at a higher frequency. If you use too small, you can get a very inaccurate measurement and get some glitch at the low frequency side. And then the shape injected signal amplitude versus frequency is very critical. So good measurement is seen here, where you could see the visible oscillation, both the output and also the switching waveform is also stable. Okay, so yeah, that's basically the 10 common mistakes that we do see in terms of DC-DC design, just to give you guys an overview. So just in summary, so we did review the common mistakes for a point-of-load DC-DC converter. So what you should definitely consider, first off, is the minimum on-time limitation of the device and the converter's ratings. So the 8 amp rating, the output current rating, even the RDS on rating of the device. Next is the inductor and capacitor selection is very critical. So you have to ensure that the inductors you select and also the capacitors you select is enough to support the device. And then compensation and startup. And then converter PCB layout to minimize parasitics and improve thermal dissipation in your device, in your design. And then output voltage and body plot measurement techniques. So we did explain why these mistakes occur and how to avoid them. So hopefully you could use this presentation as a reference when debugging and working on your new designs. And we do have some references here, so it's actually also included in the slide that you could download after this session. So all of this goes through actually more details for it. So we do have the compensator app note, as well as an E2E guide for designing two-stage LC filters, and then junction temperature measurement as well. And then for the parts that we used in the presentation, these are the highlighted parts. And so basically that's it. So different from the earlier presentations, more focused on the application side. So if you guys have any questions, feel free to let me know. So any questions from the audience? Yeah, I'll wait to start off the lunch. We're very technical right away. Okay. Yeah, if there's no questions or if you guys have any questions afterwards, feel free to reach out to me after the session, or reach out to us for any additional questions that you may have. I think we're good. Okay, thank you. So the next speaker, I think, is the next speaker.